We are now streaming on YouTube. Hi, Manasij. You are now a co-host. You know, funny thing, if you mute yourself, then the last thing that we hear before you mute yourself is the sound of you clicking the mute button. Just a fun fact.
Good to know.
Yeah, that's that's not like a deep comment about anything in particular. I'm just saying, it's a funny thing. Okay, so do you see my text editor or do you see the default Mac background?
We can see the text editor.
Excellent. Okay. Because I'm trying this out with multiple displays and we'll see how that goes.
Mela, are you finished and are you going to teach? Oh, okay.
All right, well, I hope you're ready for our second demo day. Another way to think about what these demo days are is that this is sort of, Twitch Plays Theorem Prover, referring at least to the fact that I needed you all's help, a little bit of help with Java last time around. So we'll see if your help with Lean will be equally useful. So hope you're all buckled in. You have your snacks ready. Have you noticed that if you take classes online, then you can eat snacks while you're in class? I think this is an underappreciated win of online learning. Anyway, I think it is time for us to start. So today I'll be doing another demo. And the tool I'm demoing this time is the one that hopefully you see on my screen right now, the Lean Theorem Prover. This is developed by a couple of people at Microsoft Research. It draws on a long line of other theorem provers people have developed kind of in this style. These are things like Cook and Agda and Isabel. I'm demoing Lean mostly because I think it is sort of the, if I can say this, easiest to grasp of them. So if you're interested in Lean after the fact, you should go to leanprover.github.io. That's their webpage. In the documentation, there is a whole reference manual that you can look into that can teach you a little bit about, how to use Lean, what sorts of, what the syntax is, how you can do various things in it. And hopefully what I'll be doing today is demonstrating some of the general ideas that go into this style of program verification. So at a high level, when I say this style of program verification, I'm referring to a thing called dependently typed theorem proving. And I'll be explaining in a little bit what dependent types mean, but broadly what this means is a program that can simultaneously both compute values and also construct proofs. And if you approach programming in this style, you can imagine functions that simultaneously return an output and also construct a proof that that output is correct. And as you can imagine, this can lead to some valuable software verification ideas. So for example, if you can automatically construct a proof that your function had the correct output, then you can rely on it. If you can construct a proof that the function will, if the function can always construct such a proof, then you know it always returns the correct answer. And I'll be demoing a little bit of that today. But let me start by just beginning a very simple little Lean program just to demonstrate the basic syntax. If you've programmed in Haskell or OCaml, the syntax will be very familiar to you. If you've programmed in Scheme, the syntax will be familiar to you because by now you can't see the parentheses anyway. If you have programmed in any other functional language, Scala, for example, or even like more functional JavaScript or Python, you'll see what's going on here. So let me start with by defining a little function. And this is going to be a very simple function. It's going to take two numbers. And in Lean, there are separate types for non-negative numbers called nat, and for all numbers called int. So I'm actually just for a little bit of variety gonna make these natural numbers. And so here I've written down that this is a function plus it takes two arguments, which are natural numbers, and it produces a natural number answer. And to define the function, I write colon equals, and then over here I write the definition, which is a plus b. So what's going on here is that I've defined a function, and that function is defined by a single expression, which is the body of that function. Of course, these expressions could be more complicated if I wanted them to be. So that is an equally good definition, and this gives me an intermediate variable reference. But for simplicity, since this function is so easy, we're just going to have a single expression, and that expression is implicitly returned by the function. And then you can write these functions directly in this style. You can also write recursive functions. So I can write a function that looks something like this. Now, I could write, if b is bigger than 0, then plus prime a b minus 1 plus 1 else a. But actually in Lean, it's more customary in a lot of functional languages, it's more customary to use these match expressions. So in a match expression, I give a particular value, and then I ask, what's this value like? Well, one thing that a could be is 0, in which case a plus b is b. And otherwise, it could be a prime plus 1, in which case I want plus prime a prime b plus 1. Oh. sorry. I have to define it like this. My apologies. And why you have to define it like this is some complicated now. Okay. That's right. Sorry, guys, I'm confusing my syntax a little bit here. So we'll define plus prime. It takes two natural numbers. It produces a natural number. And we can define it like so. There we go. Okay, so what I've done here is I've defined one version of plus that just directly calls the built-in addition method, and I've defined another version of plus. This one is recursive, and I've defined it via cases. So there's two cases for plus. It can have, the first argument is either 0 or it's non-zero, and so I've defined those two cases separately using some kind of recursion. So obviously no sane person would actually define plus like this, but this demonstrates that you can use recursive functions in Lean as well. So this is kind of the what Lean programs will look like. And as you can imagine, you can write sort of general functions that you might be interested in. You can sort of list in this and so on. It's a little different because unlike Daphne, you don't get access to mutation like many functional languages, but you can definitely still write most of the code you want. It's just a little different to write it in a functional style. So I don't want to spend too much time discussing sort of functional programming style, especially since it's not really the focus of what I wanted to talk about. But let me start by pausing here and answering some questions any of you may have about sort of this general idea of sort of functional programming. Let me know if you've done any Haskell or OCaml or anything like that. And remember, if you want to ask questions, just use the raise hand thing, or I guess put them in the chat. Okay, in that case, let's move on to what makes Lean actually interesting. And what makes Lean interesting, as I introduced it at the beginning here, was that in Lean, you can not only compute values, but you can also have programs that construct proofs. So let's talk a little bit about what those proofs are. So in Lean, you can declare variables using construct variable. And I'm going to start by creating a variable whose value is some kind of proof. So what I've done here is I've declared that P is some kind of variable. And in Lean, a proof and the proposition it is proving are sort of treated interchangeably. So what I've got here is I've got a proposition P, and we think of P as representing the set of proofs that P could have. So if I have two such proofs, if I have two propositions, then I can construct proofs of themselves or other propositions. So for example, I can define, I'm just going to use T for temporary as a proof of P and Q. And to construct proofs, there are just default expressions built into the language that create those proof objects. So to create an and, I use and.intro, and I make use of, we have to know that P and Q are true, sorry. So if P and Q are true, then we're going to have a proof of P and a proof of Q. And from those, we can construct a proof of P and Q. So the way you think about this is to say that P and Q are some kind of propositions. And if we were doing logic, we'd probably write these in capital letters. But because I'm in a text editor, I'm not used to doing that. And when I say that I take an argument like P or Q as, when I say that I take P, a thing of type P or Q as an argument, what I really mean is that I take something that is a proof of P and a proof of Q as an argument. And then what I'm constructing here is a proof of a related proposition that P and Q is true. So in Lean, we can refer to these expressions, which I've defined using the same def. We can also call them theorems. There's no real difference in Lean between the two, but I'm just pointing out here that I have some kind of proposition that I've proved, and I want you to think about this as a program property. So this is probably a little weird as a concept, but think about this at a high level as if this is a program that constructs a proof term. It takes two proofs as an argument, and then it returns a proof of this thing. And it turns out one way that you prove P and Q is to provide a proof of P and a proof of Q, and then call and.intro on them. So let me take questions here about this sort of weird concept I've just introduced, namely constructing proofs as code.
So is the one question here, is the proof pipeline completely distinct from the normal execution pipeline of the program?
Yeah, so you're asking basically when I run a Lean program, is the Lean program just doing computation, or is it also spending some time constructing like proofs or something? It does not, right? So the proofs exist specifically for the verification part. Meanwhile, when you actually run the program, it's just doing some normal computation. And that's sort of something you're calling out to the reader when you write theorem, though internally, Lean doesn't actually treat these two as distinct.
So these are the same language, not two distinct languages in one.
That's right. Deep down, it is the same language, but during running the program is of course not going to spend all his time constructing proofs because you don't need them. You just want the output. Other questions? Okay, so let me show you a few cases of some basic proofs that you have, some basic proofs that we can write down. So here I wrote down a proof that P and Q is true if P and independently Q are both true. It's kind of even hard to pronounce that in a way that makes it sound non-trivial. Let me write down another proof. So I'm going to call this one T1, call this one T2. This theorem is going to be that if P is true, then P and P is true. And so again, when I write if P is true, what I mean is that I take a proof of P in as an argument. And I now want to construct a proof that P and P is true. Well, we know how to construct proofs of and. We do that by and.intro, and we need to give it a proof of P and then separately a proof of P. So luckily we have those on hand, and here we have our little proof. On the other hand, so far we've treated these proofs of P or Q as totally opaque, but these themselves have some kind of structure. So for example, suppose I know that P and Q is true. I should be able to learn that P is true. And the way we can learn this is because to produce a proof of and, we have to have called and.intro. So we know that our proof of P and Q is really and.intro applied to to a proof of P and a proof of Q. And so in that case, to prove P, we have that proof on hand as well. So here we've got three different proofs that manipulate proof terms a little bit. And so far, I've basically only introduced and because to keep things simple, but we'll add a few more in just a moment. So let me take any further questions that have come up. Pranav, go ahead.
So I guess these keywords PFP and PFQ are not special, like you can call them anything else and they would be.
Totally.
Okay. Yeah, cool.
Yep. Yep, I've just been calling him PFP to sort of remind you that this is a proof of the proposition P and a proof of the proposition Q. Any other questions? Okay, so far, the only kind of proofs you've seen are ands of things. There are other things, other ways to construct proofs, as we discussed like way back in the beginning of the class. So here is another one. In this case, I want to prove the rule that people who speak Latin call modus ponens, which is that if P is true, and if P implies Q, then Q should be true. And that brings up the question of what is a proof of an implication like? Well, here we found that a proof of an and is always and.intro applied to proofs of the two sides. So here we're going to instead have a proof of an implication. And it turns out in Lean, proofs of implications, well, think about it. What does an implication mean? It means if I had P, then I have Q. So a proof of that has to be some way of taking a proof that P is true and producing a proof that Q is true. And so in fact, this proof that P implies Q term is actually going to take the form in Lean of a function. It's a function that takes in a proof of P and produces a proof of Q. Now we happen to want a proof of Q here, and we have a proof of P. So to produce that proof of Q, we can take our proof of P, pass it to the thing that turns proofs of P into proofs of Q. And that'll produce a proof of Q, and you can see at the bottom that Lean is happy with my proof. Similarly, if we wanted to produce a proof that, for example, for all P, P implies P, then I would do that by saying for any P, I'm going to return a function that takes a proof of P and returns it. So here I have the syntax for creating a function. And by function here, I mean implication. This is a function that takes in a proof of P, produces a proof of P, and therefore is a term of type P implies P. Whereas here, I am using such a term by applying it to an argument. So questions about implications? In that case, let's start talking a little bit about some kind of not totally abstract, desiccated propositions, something that has something to do with an actual program. And the first and easiest way that we can construct such a proposition is going to be equality. So suppose I have some natural number n. In that case, n equals n is a proposition. And what I've written here with the hash check, that just means Lean, show me the type of this expression. So you can see that if we have a natural number n, or in fact an integer n, or anything else, let's keep it a natural number for now, then n equals n is a proposition we can write down. So for example, 2 equals 2 is a proposition. In fact, it's a proposition we'll be proving in a moment. And also 2 equals 3 is a proposition, and we will not be proving that anytime soon. Now, to prove these sorts of propositions, to construct a proof of such a proposition, we use this weird term. Say we want to construct a proof, for example, that 2 equals 2. Lean provides one easy way of doing that, and that's called RFL. And you can try to figure out for yourself what RFL stands for, but the basic upshot is that if you have an equality between 2 equal things, RFL is the proof of that. And so that is how we can prove that 2 equals 2. But if we try to prove that 2 equals 3 with the same measure, it'll complain that reflexivity expects to prove that one thing is equal to itself, and 2 and 3 are not the same thing, and therefore it cannot check this proof card. There we go. So if we have the ability to write down propositions like this, we can now imagine combining the proposition with the actual number that we compute. So for example, we can write down a square root function with the following type. The square root of some number n, let's keep it at natural numbers, we can write down as a natural number k such that k times k equals n. And so here what I've written down is a data structure that combines a natural number with a proof. The natural number is k, and the proof is that k is in fact the square root of n. So we'll be getting back to actually implementing the square root in a moment. Maybe I should call it square root of. But this is defining a type that we would ideally like our square root function to return. So we'll end up implementing something that looks like this. In Lean, we can write sorry to mean that I'll implement it later. So questions about this idea of propositions, about values in our program. Okay. In that case, I want to introduce one more layer of concept, which is that in Lean, this notion of proofs and this notion of programs that compute things are related. And in particular, when constructing proofs, Lean knows how to compute stuff. So for example, here is a little proof. I want to prove that 1 + 1 is equal to 2. And in this case, it might seem like, well, the only way I've told you we can prove stuff is, if 2 things are the same. And 1 + 1 is, of course, the same thing as 2, and Lean knows that as well. So I can write down reflexivity here, and it'll automatically compute that. And in fact, we can even use this with this square root technique. So let me in particular do a little bit of refactoring. I'm going to say that the square root of n is some natural number whose square is n, and the square root itself will be a function from n to square root of n. So I'm going to write down a term here, which is going to prove that it is the square root of 9. And to do so, I'm going to say that that square root is 3, and that the proof is that, well, 3 times 3 is equal to 9. So what I've written here, I've created a term in this data structure that, and in particular in the data structure of integers whose square is 9. And to do so, I said that that term is 3, and that the proof involved is that 3 times 3 is equal to 9. You figured out. So what do we got going on here? Well, what we've got is we started with this idea of constructing proofs. And we've now combined the idea of constructing proofs with actual computation that our program might do, like squaring a number. To do so, when we do so, we have the ability to create terms in our program, to have our program both compute a value and also produce a proof about that value at the same time. So, questions about this? I think I'm going to wait longer than usual for questions because I think questions might take longer than usual to come up. Calvin, go ahead.
Thank you. So I was a little bit confused because I see that, sorry, I joined a little bit late, but there are like these propositions in like the types of the theorems, and then there are also propositions that you've like given to check and that you're using with like define. I was wondering like the difference between these or if they're the same thing.
Oh yeah, so when I write down, def, and then I have some kind of, proposition here. What I write down with check is basically asking Lean to tell me, is that a proposition? And so this hashtag check is really an instruction to Lean to give me additional information about what's going on. So it tells me that n equals n is a proposition. And sure enough, here we have terms that prove various propositions. I mean, I could call this theorem, and Lean actually treats theorem and definition as the same. So you can, maybe this will make it a little clearer that what I've written down here is a term, which is a proof of some proposition, namely that 2 equals 2, and that term is RFL, which is the term that proves equalities. Okay, so the big idea that I've worked up to so far is this idea of having propositions in your language, having a language that can construct proofs of various propositions, and the ability to mix computation that your code is doing with proofs about that computation, so that you have a function that simultaneously returns both a value and a proof about that value. So I want to dig into this a little more, and in particular, I want to dig into this idea of writing down propositions and then computing with them. Let me start by writing down a proposition that isn't built into Lean. And in particular, I might be interested in having a proposition about a number, which is whether or not it is even or odd. So let me start by writing down the definition that something is even. And one way to do that is to say that a natural number n is even when there exists a natural number k such that 2 times k is equal to n. And in fact, this is a fine way to write down this definition, and I can write down theorems, or let's call these lemmas because they're not that interesting. Like, for example, that 4 is even. And my proof of that will be something like, consider 2. 2 times 2 is 4. So that is my, so that is my proof. And that's one way to write down this proposition. But A different way to write down this proposition is to write it down as some kind of recursive computation. And in Lean, if we want to write down a recursive function that is a proposition, what we use is what's called an inductive type. So here is going to be an inductive type. It's going to depend on a natural number and yield a proposition. And it's going to have two branches of the inductive type, two cases in the recursion, namely that even is 0 and that n plus 2 is even if n is even. And this is, of course, going to be valid for all n. So here I've got two different versions of even written down. And we can use this version, we can prove this version of even as well. So I can say that 4 is even in this other way. And when I write down a recursive definition like this, to provide a proof of it, I have to explicitly describe the recursive nature of my proof. I'm going to actually explicitly describe the shape of the recursion. So if I want to prove that 4 is even, well, what I've got here is a way to prove that if I can prove that 2 is even, and I can prove that 2 is even if 0 is even. So I can say that 4 is even because 0 is even. And then I can take that proof that 0 is even. Oh, it's going to be. And I can take that proof that 0 is even, then say, well, if 0 is even, then this case of the recursion tells me that 0 plus 2, namely 2, should also be even. And in that case, I can take that proof and say that if 0 plus 2, if 2 is even, then 2 plus 2, namely 4, should be even. And so this is my proof that 4 is even when even is defined in this way. Now, this actually looks a lot hairier and uglier than this, but what's convenient about it is it provides us with a simple description of how any proof of even prime ought to be shaped. Namely, a proof of even prime is either even 0, a proof of that 0 is even, or even SS, a proof that n plus 2, that n is even, that n plus 2 is even, given a proof that n is even. So here you can see that this does make it kind of annoying to use for proving facts about specific numbers. But if we wanted to prove, for example, that for all n, n plus n is even, well, actually, let me take questions before I get to that. Pranav?
Can you explain this underscore notation again? Like, what does it mean? Like, how does it know that? Yeah.
Yeah. Okay. Sorry. You know, let me explain that instead of just brushing it under the rug. So the way I've defined even here, even SS, I said that it's for all n. And that means when I apply even, I need to give it the n that I intend to use. So really, this is this term.
I see.
But actually, I can figure out n by looking at the argument or even the return value that I'm looking for. And so if I put an underscore here, this even SS knows that it's being applied to a proof that 0 is even. So it knows that this term has to be 0 and it fills it in automatically. And likewise with that for 2. And actually I can tell Lean that I just always want underscores by putting little curly braces around that, and then you won't have any questions. But that's what the curly braces here mean. They just mean you can fill in this argument from the other arguments. Other questions? Okay, so the value of defining a predicate like this, a proposition in this recursive way, is that this proposition can match the recursion that the function itself uses. So for example, we can define a function to double a natural number. And one way to do that, of course, is to say that we're going to do n plus n. Another way to do that is to say that 0 doubled is 0, and n plus 1 doubled is n doubled plus 2. And you can see that in this case, the recursion in double has the same shape as the recursion in even. There's a case for 0 and a case that adds 2. And so it'll be particularly easy to prove that double returns even numbers. So to prove this theorem, I'll say, well, in the case of 0, double n is 0, and that is even by even 0. And otherwise, in the case of n plus 1, double n plus 1 is double n plus 2. So that's this applied to okay, so what's going on here? Let me expand this a little bit. In the case of 0, what we're trying to prove is that that doubling 0 is even. And we have a rule over here that says that doubling 0 is equal to 0. So this is really trying to prove that 0 is even. And this even 0 case is exactly what does so. Meanwhile, in this case, we're trying to prove that n plus 1 doubled is even. And doubling n plus 1, that corresponds to the case here. So we're really trying to prove that doubling n and then adding 2, that is even as well. Well, to do so, we can use this function, even ss, which tells us that n plus 2 is even when n is even. So now we need to construct as an argument a proof that doubling n is even. And we can do so recursively by calling the double even function that we're defining itself. So this is our first inductive proof. And you can see this is really just a case of constructing a proof by recursion. We're recursing over n, decreasing it every time until it gets to 0. At each point, we can construct a proof starting from our proof that 0 is even, and then building up by steps of 2. Questions? Okay. In that case, let's do one more theorem about even numbers. In this case, I'm going to prove that adding even numbers yields even numbers. Okay, so what I'm writing here is that if I have two natural numbers, both of which are even, then their sum ought to be even as well. And we'll do this again by looking at cases. If n is 0, then we are looking at, and here, instead of writing out these comments that I expect you to follow, I'll just use some lean syntax that allows me to write them out directly, and that's called calc. So I'm going to start with, oh yeah, and I'm going to have the proof that n is even and the proof that m is even. So here I'm going to say, I'm going to start with a, actually, okay, no, sorry. So what am I looking at? I'm trying to prove that n plus m is even. And in particular, I know that n here is 2. So I've got 0 plus n. Actually, let me do this. So I'm looking at, I've changed it to m. So I'm looking at m is 0, and I'm looking at trying to prove that n plus 0 is 0. Well, of course, n plus 0 is equal to n, and I happen to have a proof that n is 0, namely the proof that n is even, and that is right there. Then I've got the other case, which is now I'm trying to prove that n plus m plus 1 is even. And that, of course, is a proof that n plus m plus 1 is even. And unfortunately, this doesn't help that much here, because it turns out that I have no way of going from a proof, I have no way of constructing a proof that n plus m plus 1 is even, because evenness goes up by steps of 2. So instead, it looks like I can't clearly make headway here. Neither increment by 2 nor the 0 case applies, because I don't know whether this is 0, it's definitely not, but I also don't know that it's 2 bigger than some number. So to help with this, I'm going to specifically look at this simpler case where n is increment by 1 as well, is at least 1 as well. So this way I get n plus 1 and m plus 1. That should give us n plus m plus 2. So I should be able to apply okay, so let me pause here before I continue to deal with this type mismatch to answer any additional questions y'all may have had as I go through this proof. You know, I think I need to take this, the lack of questions as meaning one of two things. Either it's really sunny out and you'd rather be out there, which is fair. I mean, the lecture is recorded, so have at. But the other thing is that people are sort of confused what we're even doing here. So why don't you, let's do this. Let's say click the raise hand button if you are confident you understand what's going on and why we're doing it. All right, that's not a big vote of confidence. So if you didn't raise your hand, what's going on? What are you confused about? Okay, we got a question in the chat. What are these PFNE and PFMEs? Yeah, sorry, this is my little abbreviation. Proof that N even, proof that M even. You can see that as we've defined plus even, it takes arguments N and M, and also a proof that N is even and a proof that M is even. Remember that anytime you have an implication like this between two propositions, another way of thinking about that is as a function that takes in proofs of the propositions as arguments. So here, this function actually has 4 arguments, N and M, and then these 2 proofs, and it produces a proof on its own. Other sort of general questions about like what's going on and why we're doing it? Now is the right time to admit you have no idea why we're doing what we're doing. Okay, well, in that case, I have no choice but sort of continue trucking on. So here we've written down what looks like a pretty solid proof that adding even numbers yields even numbers. Lean has a few complaints. It says, I didn't consider the case of 0 plus something. That's fair, that's easy to add. I'm going back to my short forms. I got to type these live, so. You know, my apologies. So now we've handled all the cases. However, Lean is still unhappy about some stuff. And this is gonna dive a little bit more deeply into this idea of mixing computations together with proofs. So if we look at either of these 2 complaints, like say this one, we see that Lean is complaining that I have produced a proof that M is even, but it's looking for a proof that 0 plus M is even. And actually this other complaint, this other red squiggly, has a similar form. It's saying, I'm looking for a proof that something plus 2 is even. What I have is a proof of something plus 1 plus something plus 1 is even. Both of those are pretty weird complaints because like there's a lot of things computers are bad at, but math is not one of them, especially like adding small numbers like 0. And this goes back to how Lean is able to do how Lean is able to deal with computation that happens inside proofs. So for example, here, in order to prove that 1 plus 1 was equal to 2, Lean had to do some kind of computation, namely add 1 and 1 together. But on the other hand, there's some kinds of computation that it's difficult to see how Lean could directly do. So for example, here is a proposition that you might write down. In fact, it's a proposition that we think is true. However, if we try to prove it using the one method we know how, namely REFL, it will complain that it has no way of knowing that P plus Q and Q plus P are the same thing. And that, if you really try to have some like empathy for the computer, makes sense because what it knows how to do is how to add natural numbers. And P and Q aren't natural numbers, they're symbols. In particular, the way that plus is actually defined deep inside Lean looks kind of like this definition here. And so in order to add 2 numbers, Lean must first figure out, is the first number 0 or is it bigger than 0? And here, Lean does not know. than 0 or bigger than 0. If we were to add cases to this definition, so for example, to look separately at the 0, 0 case, now we're trying to prove that 0 plus 0 equals 0 plus 0, and Lean actually does know how to do this sort of definition. So it can say, in this case, I know how to add 0 and 0. I'll get 0 on both sides. I can prove this with reflexivity, with RFL. But in the general case, Lean does not actually know how to do so. So what I'm trying to explain here is that in order to do computation while it is checking proofs, Lean has some rules about how it does so. Namely, if I just have an abstract number like P, Lean can't exactly compute with it. You know, who knows what number it is. And so specifically, that means that when I'm doing a computation like 0 plus m, Lean doesn't necessarily know how to compute that to m, specifically because it's looking to find out what the right-hand side of an addition is before it can do the addition itself. So let me pause here to take questions on this kind of weird concept that I'm trying to explain. Okay, so if we want to prove facts like this, or actually let's go simpler. If we want to prove facts like 0 plus n equals n, we need to have some other way of doing so. And in particular, we need to have some way of doing so that lets us deal with specific cases of n, not n in general. So Lean provides basically a single method for doing so, which is this kind of pattern matching construct. And this pattern matching construct will end up involving some amount. Well, we'll see in a moment. So here what I've done is I've asked Lean to first consider two separate cases for n. One where n is equal to 0, one where it is equal to n plus 1. And in the 0 case, what we are trying to prove, and this time I can write it out with calc, we are trying to prove that 0 plus 0 is equal to 0, and we can do that by reflexivity. Hello? Okay, sorry. Well, let me just keep going. So what we're trying to prove in this case is that 0 plus n plus 1 is equal to n. And I'll do that by a couple of step-by-step operations. First, since to do addition, Lean wants to know whether the right-hand side is 0 or not. We've now discovered that that right-hand side is not 0. So that allows Lean to do one step of addition. So this will produce 0 plus n plus 1, which is how addition is defined analogously to all the way up here at the top. And so this step Lean does via computation. Now, you can see that we have a term that looks much like the input to the theorem we're defining. So we can actually apply this inductively by saying rewrite with plus c. And then n plus 1 is exactly the right-hand side here that we want to produce. Remember that we've discovered that n is the form of something plus 1. And so this definition convinces Lean that the results are correct. And you can think of this again as being some kind of recursion where we apply plus c, we had n plus 1, and now we're applying it to the one smaller number n to construct this proof. And that should actually allow us to say that we want to apply that, let's see, let's get back to this. Let me take questions first. So I've written down this definition where in order to help Lean understand how to do basic math on numbers, we've had to look inside what this right-hand side n is. And then upon discovering that it is either 0 or bigger than 1, Lean can actually proceed by doing a little bit of math. And that allows us to recursively construct the proof we want. Questions? Yeah, go ahead, Pranav.
So I was thinking about the case where in the theorem plus underscore even you were trying to prove that m plus n plus 1 is even or not. So it seems like Lean is storing the information that it is able to prove that something is even. Does it also have sort of construct where it is able to store the information, where it is able to disprove that this is even, and then you can negate that proposition and say that it is odd, and then you can reuse it in the plus underscore.
Oh, sure. So you're basically asking like, how do you deal with negation? And let me show you a sort of simple case of how that is. So suppose I know that P is true, and I want to prove that P is not true, which is like, I don't know, some logical thing. Well, in fact, the way that proofs of the negation of P work, so here I'd have an argument that P is true, and I want to do something with it. The way you prove a negation is by contradiction. Specifically, you assume the thing is true, and then you prove that that would be ridiculous. So here, let's assume that not P is true. And now I want to derive some kind of ridiculous contradiction. Well, the proof that P is not true is itself a function that takes in a proof that P is true, produces an absurdity. So I can apply that proof to my proof of P. And so what this is doing, this is a proof of P. I am using not P to derive a contradiction. And that contradiction is what I wanted, which is if P were not true, then there would be a contradiction. Another way of thinking about this is to say that not P is actually defined by something like that. And so here I have this argument is a function of type P2 contradiction. And I apply that function to my proof of P and get the contradiction that I am supposed to return. Does that answer your question?
Yep.
Okay. Other questions? Okay. So I've shown you how we can sort of help how this notion of computation works inside Lean, namely how Lean knows how Lean can add numbers automatically inside a proposition statement. And it happens specifically by looking at what is the case of this right-hand side for addition or whatever other variable that this function recurses on. And so in the case where we actually need to do this recursion over an unknown value, we have to apply this sort of case split to discover what that value is. And then on each of those sides, we can actually rely on Lean doing some amount of computation and then combining that with recursion to actually prove the property that we want. And so we can take this and try to apply it over here. So I actually, let me pause for just a little more questions about this in case people have, want to ask something about getting back to this idea of proving that doubling something is even. No? Okay. In that case, let's get back to fixing up the proof that we started but didn't complete here. So, and that's going to tell us a little bit about how to use equality. So here, we would like a proof that m is even. Oh, sorry, we have a proof that m is even, but what we'd like is a proof that 0 plus m is even. And naturally, we've gone ahead and written down a proof here that 0 plus n is equal to n. So we'd like to somehow use it. The way you use that in Lean is via substitution. So remember a long time ago, we were talking about first order logic and how we write down the theory of equality in it. And I mentioned that there are basically two things that you can do with an equality. There's the identity rule that anything is equal to itself. And we've seen that reflected in this RFL construct. And then there's the substitution rule, which is that if you know two things are equal, you can use one in place of another. So we have here something like, so plus CM is our proof here. Oh, and it looks like plus CM is working in the opposite direction. It's taking the proof of M is, it's allowing us to produce, it's expecting a proof that M plus 0 is even. So I actually need to do this in reverse. So I can use eq.sim just to flip this equality around. So you can see that eq.sim here, it just takes an equality A equals B and produces an equality B equals A. So I have my proof here that 0 plus M equals M. Reversing, that's a proof that M equals M plus 0. We have a proof that M is even. And if we substitute M to M plus 0 in it, we get a proof that M plus 0 is even. Or actually, sorry, 0 plus M is even. So this is how we can use equalities. Specifically, we use substitution to use equalities in our proof of other things. So questions about this, and then we'll do something similar with the other case of plus even that we're interested in. Okay, great. So we want to do something similar over here. Remember that the problem here is that we have n plus 1 plus m plus 1, and we want to turn that into n plus m plus 2. I'm going to write this out as its own lemma. And learning from last time, I'm going to write this in reverse. So this lemma will work in a similar way as above. We will look at two cases. So in the first case, we have something plus 0. And in the other case, we have something plus m plus 1. And in this case, again, we're looking at proving we are starting from n plus m plus 1 plus 2, which is equal to, because we can now do some computation, n plus m plus 1 plus 2, which we can rewrite to, actually, let me actually say that this is equal to, no, hold on. Let me roll back to here. So we're starting by stating what we've got, which is that this with m plus 1 substituted in. What we're trying to prove is that n plus 1 plus m plus 1 plus 1, that these two things are equal. And so our question is how we can prove that. I'm going to prove it step by step. Those pop-ups are kind of annoying. So we'd like to rewrite this into this form. And we can do that by working backwards. So this is relying again on the fact that when I do addition and I know some fact about the right-hand side, I can expand that addition. And is this happy? No, this is not happy, sorry. Oh yeah. I just screwed up my addition. Okay, so now I've rewritten it into this form. And oh. I think what I wanted was something like this. Okay, my apologies. I seem to have somehow gone off course from where I was supposed to be. So I don't want to spend all of my time debugging this. Let me just replace this computation. I'll upload the fixed version once I figure it out. My apologies there. But again, we've got this. What we were trying to do was, again, write down a little lemma about addition. And now, again, we can use that lemma to do something like this. All right. I think that is complaining because I've not actually defined that, but I'll fix that in post. My apologies. what I wanted to basically demonstrate here was the ability to use equality, equalities that we've proven in some other way in our proof process to rewrite facts into equal form. So this here has the type that n plus m is even, and that should allow us to, oh, I see what it's unhappy about. And that should allow us to conclude that n plus m plus 2 is even. So so that's what I was trying to do here. So I'll fix this up in afterward. Let me take some questions about what is this ID? What are we doing here with this combination of equality and induction to write down proofs of propositions? Okay, so just to rewind, what have we talked about today? Well, I've introduced this language Lean, which is from first look sort of an ordinary functional programming language, but it's a language that mixes computation with this notion of proofs of propositions. So you can have programs that compute numbers, but you can also have programs that construct proofs of various propositions. And the cool thing about that is that we can write down data structures that combine some data together with a proof of them. So it's no longer so much that we build a program and then separately prove that it's correct. The program constructs a proof of its own correctness as it goes. So that's sort of the big vision here. And then to make that vision a reality, we've talked a bit about some of the details that go on underneath. So this idea of writing down propositions as something that you can prove by induction. So like here we can prove evenness by induction, by proving that 4 is even, by first proving that 2 is even, and so on. And we've talked a little bit about how we can construct those sorts of inductive proofs by using induction ourselves, or by using recursion ourselves. So here we have plus even that recurses on itself. So that's the big vision. That's what we're introducing here. And I wanted to give you finally a sense of how this sort of thing could be applied to build a real function. Square root is not that real a function in that like probably math.square root is what you'd actually call, but I want to show a little bit about how you might write a function that combines induction and proofs of programs together with some real computation. So my implementation of square root is going to be kind of dumb. I'm going to do it in a function square root helper, and square root helper is going to have 2 variables. It's going to be my functional programming equivalent of a loop. It's going to have n and k, and it is going to produce a square root of n. Now, if you think about it, in the natural numbers, not every number has a square root. So I'm actually going to have to refine this type signature to tell me that it'll either return a square root of n, or it'll just complain that no such thing exists. So that's what option does here. So how will this sort of thing work? Well, I'll do it again by cases, and think about this argument as the number we're taking a square root of, and this argument as the number we are testing as a possible square root. So here we start with 0, and we can ask if n is equal to 0. Well, if n is equal to 0, then 0 is itself a great square root. So we can write sub type dot make 0 REFL. And since we had option around it, we've got to do something like that. Oh, it's scrolled way up, sorry. Huh. Oh, I see. I switched tabs. That was confusing. Those are my before class notes. And otherwise, there's no square root of n, because the way I want to think about this is that I count down from n to 0. Okay, we'll get back to that in a moment. Otherwise, k is some k plus 1, in which case we say if k plus 1 times k plus 1 is equal to n, then in fact, let me not even write REFL here. Let me just write an underscore so that we know that we have to get back to it. Okay, so here I've written down just sort of the skeleton of the program. To count a square root, I first check if n is a square root of n, and then n minus 1, and then n minus 2, and then n minus 3, and that's accomplished via this recursion. So I've got a base case at 0, and then in the k plus 1 case, I recurse to the k case, unless I find the square root itself. And then, I gotta do this thing where I actually look at the square root, and if I actually squared my test number, k plus 1, and if that's equal to n, then that is my square root, and otherwise I do some other thing. And what I need to fill in here, yeah, that seems fine. What I need to fill in here, there we go. What I need to fill in here are these proofs. So remember that the subtype.make, it gives us the actual square root we're looking for, and then separately we need to give it our proof that it is a square root. So to do that, we need to think a little deeper about this if statement. Remember, one thing that we've emphasized in this course several times is that if you go down a particular branch of an if statement, you've learned something, namely that the condition you tested is actually true. And in Lean, this sort of knowledge is in the ordinary if statement kind of hidden. You check this condition, but then you throw away the actual knowledge that you learned the proof that say n is equal to 0. But we can extract that proof using a term called DITE. Don't ask me why that's the name. So this term takes arguments it takes arguments, and the arguments are passed either proofs that the condition is true or proofs that the condition is false. So here I'm passed a proof that n is equal to 0, and here I am passed a proof that n is not equal to 0. And so in fact, using my proof that n is equal to 0, what I'm trying to prove here, remember, is that k times k, or 0 times 0, is equal to n. And I have a proof that n is equal to 0. So what I really want to do is use something like, well, take my proof that n is equal to 0, and we can see that it's the wrong direction. So flip it, that gives us a proof that 0 is equal to n, which is exactly what we're looking for. 0 times 0 is 0, that's equal to n. And similarly, we can transform this code here to, instead of just doing a computation, to pass proof terms along as well. So here I have my proof that here I have my proof that k plus 1 times k plus 1 is equal to n, and I can make use of it here. And in the other case, I will get a proof that k times k is not equal to n, which I will ignore and just do the recursion. And you can see that the end result of this is that I end up getting a successful result. So this whole program type checks, and I think there's probably some, Lean requires these to be ordered in the file. And that gives me now a square root program that again is not only computing the square root of a number by sort of testing each number below n, but it is doing so while also passing around these proofs and making sure to return that back to the caller so that the caller knows that the number that's been computed is in fact a square root of n. So this has been kind of what I wanted to show you. Just introduce this general idea of programs that both compute values and produce proofs. I know that some of this has seemed a little weird and I had to discuss some of the stuff at a fairly high level. As you may recall, our last demo was after I introduced all the theory, and this one is before I introduced all the theory. So if this seemed a little unclear how this all works under the hood, don't worry. I'll be talking about that for the next 3 lectures. But I'm happy to take any questions you have now, conceptual or detailed, about what it is we're trying to do and how it is we're doing it with this when we make use of this idea of code that constructs proofs and also computes values at the same time. Okay, Hao-Chen?
Hi, I want to ask, what does this option sum and option none do?
Oh, yeah, sorry. Okay, that's I should have introduced that. It works like this. An option of A, where A is some type, is either, let me just, I'm just renaming it so it doesn't tell me problems about it conflicting. So there are 2 kinds of options. Either, sorry, don't have the thing, or if I do have such a thing, that is also a solution. That is also an option. So you can think of this as like a nullable type in Java, where something is either null or it is not null, and then in that case you have a real thing of that type. I'm using it here because the square root of the square root of some natural numbers doesn't exist. So I'm not going to be able to write a function that ever returns a square root of 3, because no natural number squares to 3. So that's what this option is. It's basically saying either I get a square root of 3 or I don't, right? And you can think of this kind of like a nullable square root of 3 if you want to think about it that way. Does that answer your question?
Yeah, that makes sense.
Great. Other questions? Bradley, go ahead.
Does this technique of computing proofs and having proofs be terms in a program mean that Lean is more powerful than Daphne or can prove more things than Daphne?
I mean, okay, so I would say it is a different style of verification. Often this kind of thing is called proof carrying code, namely code that produces output and also proofs about that output. This is a bit of a different perspective, right, from Daphne, where you write the code and the proof is kind of separate from it. They're not integrated like the way they are here. But I'm not sure that, in general, this kind of difference doesn't have to mean any difference in proof strength. There is some kind of like subtle theoretical notion of how strong a proof system is, which is not particularly relevant to ordinary life. I think in terms of like stuff you might actually want to prove facts about, both Lean and Daphne are equally powerful, even if there might be some kind of like vague mathematical set theory about, you know, one having more inaccessible cardinals or something. As a concrete example, Daphne and Lean have both been used to produce verified crypto libraries. So at least to the extent that, you know, crypto libraries are complicated, they involve some pretty hairy math and also some pretty hairy code. Both Daphne and Lean seem equally capable of doing that. Other questions? Well, if not, our next 3 lectures will be looking at the internals of something like Lean and this notion of code that computes values and also produces proofs about those values. I will be putting the demo code online as soon as we end this, and also I fix those bugs that I promised to fix. And before next time, please make sure to fill out the course feedback on Canvas. You're all on a computer right now, so right now is a great time to do so. The lecture is still fresh in your head. If you felt completely confused, that is one great way to tell me about it. And otherwise, I will see you all on Tuesday, where we will be talking about the Curry-Howard isomorphism, which is a long and portentous way of saying, what are proofs like? So see you all on Tuesday. And I'm happy to take any additional questions y'all have.
So this square root. So can you share the screen again?
Oh, sorry, I just exited that. Go ahead.
So the square root helper in line 56, if I get it correct, like is it like first you give the argument n to the square root helper in line 56, and then it returns a functor, which is again applied to the argument n. Is that right?
This is, yeah, okay. So what's going on, you're basically asking what's the difference between this n over here, this nat over here, and this nat over here. And all I'm really doing by writing it on this side is I'm saying it's not going to change as I do my recursion. And so that that means that I don't bother to write it over here. And you can see that, again, we don't pattern match on here either. What I could do is I could instead write it here and then pattern match on it over here while not actually doing any kind of pattern match, and make sure to invoke it in the recursion here. And there's probably something dumb going on, but I bet I could fix these bugs.
I see. Okay. Yeah.
Yeah, that's probably something about me not doing the transformation perfectly, but that's the basic idea. Other questions? Yeah, go ahead. You're the only one left, so you can just unmute and.
Okay, I'm waiting this moment. So I'm doing the final project and recapping on the lecture 14, and I feel like I